Hey guys, welcome back to Project 2, your Marshmallow Blaster. I have truly enjoyed looking at your lightsabers, your creativity, and some of your customizations are pretty impressive. So I can't wait to see what you guys come up with for your Marshmallow Blaster. Now, this one's a little bit different because I broke this one into two pieces as far as Jedi training because there's some information here that we were not able to cover in class due to the situation. But this is such a really cool project, and it's one of my students' favorites from the past, and I wanted to make sure that you guys got an opportunity to do it. So with the Marshmallow Blaster, you were challenged to come up with some type of machine, specifically a compound machine. Um, to help destroy the Death Star once and for all. Now, to be able to do this, you had to understand simple machines and Newton's three laws. Now, what I did for you is I attached the readings into Google Classroom. You really don't need the readings, not unless you're on paper, but if that's what you prefer, that's fine too. But what I've done is I've given you video links to help you, and each of these links will break down for you. They have like a little quiz in there. It's very kid friendly to where you guys can pause the video, write down definitions. It's really, really, really nice. So I purposely picked those to help you. If you're struggling with how to answer any of the questions, for this assignment, this is what you want to come to. So if you've not done Jedi Training Part 1, um, or part 2 here, if you've not done this part, you need to stop, do this before you actually draw your marshmallow blaster, okay? And try to answer the questions at the end because it will not make sense, okay? What I want to do is kind of go over what I'm expecting and to kind of help you here with simple machines and especially Newton's laws, okay? For simple machines, what I'm looking for you guys to do is just to give me, well, what is it? What does a pulley do? Well, this is like the flagpole. You pull a rope, okay, and it kind of distributes the weight, like the force, right? You're pulling on one end, it lifts the other. So I would kind of put that in my own words, and then I would put my example is a flagpole, okay? Use things that you know. A lever. This is a seesaw. Okay. This means that they have a fulcrum. In other words, it has a nice little triangle to where it actually bounces on. Your scales are like this. Inclined planes. This is like your handicap ramps. Anything, your door wedges, anything that's at that slant. Okay. A wedge, think of a door wedge. Okay. You're actually pushing or prying two things apart. A screw, well, it's nothing but an inclined plane wrapped around a pole, basically. Okay? And you know what a screw looks like. You probably can go into a toolbox around the house, into a drawer, go look at the furniture, and you can find a screw. You guys are at the age you're driving, or at least you're interested in cars. You should be able to tell me what a wheel and axle is. Okay, that's kind of an important part of a car to make it go. So these are things that you're really familiar with. Don't overthink this part. What I'm challenging you to do is to take four of these, four, not all of them. I'm going to say that again. Take four and turn this into a compound machine. A compound machine is where you take multiple simple machines. So you take more than one of these and you mush them together to perform a job. That's what you're doing for this activity. You are building a marshmallow blaster, aka a catapult. Okay, you can Google catapults. Some people have went and made like potato guns or marshmallow guns. That's fine. You can take it in that route. Most kids will do the catapult because it's easier to actually get those forcible machines in there. I have attached a picture of mine in Google Classroom so that you can kind of see what forcible machines I used and kind of how I did it. But all you're doing is picking four of these, mushing them together so that it can flick a marshmallow and take out the Death Star. Okay? Because normally what I would do is I would actually have you guys shoot marshmallows at this inflatable Death Star and you'd have to hit a target. We can't do that. So we're hoping that you can design a machine or a draft of one that could actually perform this if we were to build it. Remember, that is not a requirement. You do not, I'm gonna say that again, you do not have to build this. Okay. Part of your written portion of this assignment is not only to draw your marshmallow blaster and identify the simple machines and kind of tell me how it works, okay? But it's also to explain to me how your machine or this whole taking out the Death Star, this whole process demonstrates Newton's three laws. So what I want to do is I just want to make sure that you have those 3 laws, okay? The first law of Newton's states that an object in motion, and apparently I can't spell again, guys, sorry about that. An object in motion will stay in motion. Or an object at rest will stay at rest unless it is acted upon by an outside force, okay? So think about this. If I kick a ball, that ball is going to continue to move according to Newton's laws unless something or some outside force acts upon it to stop it, which we know that it's running up against the grass. It's going to run into things. There, friction, it's going to slow it down. There is a force causing it not to stay in motion. That is why it stops, okay? The same thing applies when an object at rest stays at rest until acted upon by an outside force. Your book's not going to grow legs and walk across the table. The only way that book's going to move if you apply a force to it to make it move. Okay? Now, all of this revolves around this idea of inertia. Inertia, as Bill Nye says, is a property of matter, but what it says is that an object wants to stay in motion. In other words, if I'm going forward, I want to keep going forward. I don't want to stop, okay? And seat belts are probably the best example of this. This is why I actually ask you this question. When you're driving in a car, you're moving at the speed of that car. When you slam on brakes, what happens to your body? Your body flies forward, okay? What does your seatbelt do? Your seatbelt is a force acting upon you. Inertia is saying you want to keep moving, but the seatbelt prevents you from doing that. If you're not wearing your seatbelt because of inertia, you would fly out the window, okay? Because your body wants to keep moving, okay? So simply put, inertia is an object, or an object, should I say, wants to keep moving or traveling in the same direction. Okay? It wants to keep going the way it's going. It doesn't want to change. Okay? Now, that's Newton's first law. Okay? An object in motion will stay in motion. An object at rest will stay at rest unless acted upon by an outside force. Law 2 states that there is a relationship between the force applied to an object and its acceleration. To be honest with you, this is kind of common sense if you think about it. If I hit something harder, it's going to go further. If I kick a ball harder, it's going to go further. Now, the only catch in this is that what happens if I increase the mass? So think about this. What would happen if I kick a bowling ball? Is it going to go very far? No. Why? Because it has more mass. So when I increase the mass of an object, you decrease the acceleration, okay? The only way to make that object accelerate would mean that because it's heavier, I would have to increase the force. So if I increase the force, you increase the acceleration. If you increase the mass, you will have to increase the force. Why? If it's heavier, you're going to have to put more effort behind it to make it move. Okay? So this is that whole direct, indirect relationships that we've talked about in the past. Here, what Newton is saying is that force equals the mass times the acceleration of an object. Okay? And I think I accidentally, yeah. So force equals mass times the acceleration. So the heavier an object is, the slower it's going to go. To make it go faster, I have to increase the force to increase acceleration. When I increase the mass, you have to increase the force applied to make it move. All right. The final law states that for every action, okay, or for every force, there is an opposite and equal force applied. Okay, you guys have probably heard the whole saying, for every action, there's an opposite and equal reaction. The same thing here. If I am applying force to something of this much force, of this much energy, that same amount is being pushed back against me. Think about propping up on a wall. If I prop up on a wall, obviously I'm applying force to the wall. I'm pushing against it. But there has to be an opposite force. If the wall was not applying a force back, I would just fall through. Okay? So for every force, there's an opposite and equal force. The same thing applies to like a chandelier hanging from the ceiling or a ceiling fan. Gravity is pulling down on all objects. We know this. We learned this in Unit 1. Okay? But that's the force being applied. What's actually keeping that object hanging then and not just crashing to the ground? It's the opposite force. The opposite force would be the chain that's actually holding the light into the ceiling. Okay? So the force being applied is gravity. The force of the opposite force pushing back is the chain that's connected into the wall. Okay? Now, what's really important to understand is just because there is an opposite but equal force applied, it does not mean they're balanced. In other words, it goes back into this whole math thing. If I push an object, just because I push it, it doesn't mean it's necessarily going to move. Okay? Because it's going to apply the same force back to me, but because of its mass, the object may not move, and that would mean it's an unbalanced force. Okay? So that's a really quick overview. I know that I said a lot in a very short amount of time, but go back and look at those videos, because now what you're going to do is you're going to take those 3 laws and explain to me how they're demonstrated with your marshmallow blaster. For example, Newton's law says that in number 1, we'll just do the first one. For every object in motion that will stay in motion, an object at rest will stay at rest unless acted upon by an outside force. When I pull back, okay, to release my marshmallow, because I made a catapult, and you can see that in the drawing that I attached in classroom. When that marshmallow goes flying, Newton's law is being applied. That marshmallow is going to continue to travel until it reaches, well, an outside force, which hopefully, if I did it correctly, it will actually hit the Death Star, okay? Which would be the opposite force, or the force acting upon it to make it stop, okay? But because of inertia, it wants to keep traveling. The other thing is an example for number 2 is, I'm going to use a small marshmallow. Why? Because if I decrease the mass of my marshmallow, the further it can go. So the less force I'm going to need to apply to make it accelerate. Those are just 2 examples. If you need additional help, let me know. But this is kind of my quick overview, guys, of Project 2. Make sure that you read the rubric very carefully. What should be on your drawing? Look at my example and answer the reflection questions so that you can submit this for your project grade. All right. I'm ready now to move on to project 3. Remember, I'm always here to help you. All right, bye guys.